Thursday, and then the Thanksgiving break. When we come back, there's only 3 lectures left. So I want to ask you, will you be interested in me spending some time in class, maybe 20 minutes or half an hour, and give you a presentation regarding career advisors, graduate school, entrepreneur, job, etc.? Do you care?
Yes.
You do? Good. That's what I hope. So I would find a convenient time to do that. I don't know when yet. It depends on the lecture, how we're progressing. But I will make a note of that, and I think you'll enjoy it. It's an interactive type discussion, but I think it is something from past experience very beneficial for your planning. So today, back to the core discussion. The agenda is deep dive in differential equation formulation. It's very, at times, dry. And it's like I'm floating you at the deep end of the pool and then you either swim or sunk. So what we will do is to just look at something called vector notation. It allows us to simplify the presentation of all these differential equations of continuity and momentum, which consists of the Eulers, which is implicit, and Navier-Stokes, which is the holy grail, which is the most comprehensive equation in fluid mechanics. And this is important also that allow us to look at the physics of those very complex equations at a very high level. So while it's a little bit of calculus and mathematics, bear with me, because we will pay dividend later. And then for the much of the lecture today, we are focusing on the use of differential equation of continuity. I will first present the equation, show you how you use it. That's your homework for Thursday. And then I'm going to finish by going back to show you how to derive that equation from the ground up. And that's the part that is a little engaging. I hope I have enough time at the end to continue on and look at the Eulers equation of motion in 3D. So you've seen that in streamline coordinate, N and S. Now we go generalize it in 3D and account for gravity and account for unsteadiness. So it's really complex, but I think once those are done, we can continue on and find out how one can solve those complex equations either by pencil or paper or on the computer, which is what you do for your career. Assignment, the posting is done yesterday. That's a 3-page handout. I'd like you to bring it up on your computer so that you don't have to copy, because a lot of what I'm going to present today is on that. So you can just make notes. Instead of busy copying, you can just pay attention to me. So I will always use this symbol N and S. That stands for Navier-Stokes. That's the equation that we are homing in. At the worst case, by Thursday, and then you have all the equations you need to study fluid mechanics. Homework, hour and a half, because those are very elementary problems. Chapter 9, going back to those equations of laminar flow, calculating stress, shear stress, and calculating drag, etc. Very number, plug and chuck type number problem. Chapter 6 is what we're dealing with today, differential equation of continuity. So I will touch on that as we finish presenting the continuity equation. Set of homework after Thanksgiving break. The inclined plane problem is very engaging and intricate, and I will post that for prior to Thursday lecture. On Thursday, we will engage in looking at what that problem is and how you can use viscous equation of motion to solve that. Any question before I start? So we have looked at the quantity on the far left, to your left, that is. Oh, before I start, you have done the homework today, right? All of you, and the quiz will be returned to you maybe next lecture, right? Yeah. When you do the homework, assume, any question on the homework today? I assume it's pretty straightforward. Have you stopped and asked yourself, is there something wrong with this equation that was presented to you in the book? Do you see anything that make you kind of uncomfortable? And I put a question mark there. No? Nothing come to mind? I always stress unit homogeneity, meaning the equation can always have apple to apple. Yes?
The z terms, like with the I and normal to x.
I'm sorry, I can't hear you.
The z terms with I and normal to
No, that's not it. This can be, this term in this bracket can be x, y, z. Remember, we're in 3D. And what this is to prescribe to you a velocity vector. That can be a function of time, can be a function of coordinate x, y, and z. So there's nothing wrong with this. Nor this, nor this. All right, yes?
You have like 5z, and that z is in terms of meters.
Right.
So you go.
So the unit is not consistent. Right, that may caught your attention. It turns out in all this numerical scheme, all you're looking for is strip the unit. Okay, in the way it's applied, the unit is not, need to be, in our conventional sense, consistent. And all it is just an algebraic expression in terms of time, x, y, and z. The unit is not carried in a way that we have looked at in the past. So I thought I would bring it up, just so that you don't get confused. And when we move forward, that will happen again and again. Yes?
So going back to what you were saying with like the z and the I terms being together,
C in the item, yes?
does that mean that velocity in the x direction depends on z?
Exactly.
Okay.
That's how it should be read. Absolutely. Right. Okay? So those are just very elementary problems just to get a sense of what we meant by this guy, which is what we talked about last time. And that is kind of our building block. This is acceleration. And when we are done, after all that math and algebra, I'm going to tell you it's nothing but F equal to ma. And here's the A. And that will come in about 40 minutes. So you'll be down on you and say, wow, after all this time, it's nothing but Newton's second law. That's correct. There's nothing wrong with that. Go in full circle. Yes?
If we give units to like 5 and 3, to say 3 is like meters per second and 5 is like 1 over second,
Mhm.
it works. The equation to derivative time acceleration, can we use that to check if we got it?
Yeah, if you really want to dive into it, you can make it work. But for simplicity, the way it's done numerically, you strip the unit. All right? I have to say this is academic. This is, just some problem to warm you up to the idea. In numerical scheme, it's no different than that. All right, so we look at this equation. I want to revisit it because it will be the starting point, and it's very important to understand the physical interpretation of this acceleration. So on the left-hand side, what kind of acceleration we call this? I have given a name to it. You need to remember this because I can bet you dinner. A year from now or in the fall, you come back and you have heat transfer in your junior year, and the professor says, have you seen this kind of notation, the Navier-Stokes equation, and convective acceleration? I bet you lunch, 5 out of 10 of you, maybe more, you say, never seen it. Right, okay? So I just want to state that up front. What is this acceleration? Substantial or total? Total because of this term on the right, which consists of local time-dependent acceleration, and most importantly, what do you call that? Huh? Spatial or convective is a kind of more intuitive term for the fact that it come about because of the flow moving through a device, right? A nozzle, that's the classical example. Any question on the come about this equation? Now this can also be written in general as a total derivative, whereby I have removed the velocity term. So this becomes now a total derivative that can have other applications beyond fluid mechanics. Any question on this acceleration? So when we deal with fluid, acceleration is a little bit more complex beyond just rate of change with respect to time. Now this is equation on top of here with the vector v. How many actual equation is being represented by this vector v? This is how we started with chain rule, remember last time. But inherent to this one equation How many equations can be written up? 3. Very good. That's why I want to take on to the next step. The 3 are x, which is u velocity. And this is not on your handout that I gave you, so if you choose to, you may want to just drop it down on your notes. So of the 3, here's the first equation in the x direction, and the other 2. Y. How would you write that equation? Can you infer from what I have done here? And tell me what are the missing terms? Remember, I'm using this operator, or total derivative. I apply that to the x direction, which consists of the velocity u. Now I am in the y direction. What component of velocity would be of interest there? What's missing in the numerator? Anyone? It's the v. Then lastly, I have the third equation, z. So v here. Oops. And it's just repetitive. And it would be nice if I can have a convenient way to write this equation by vector notation in a much simpler form. So in the W component parallel to Z, I have this equation of x, y, and z. So a vector equation actually consists of 3 pieces. Any question on this? This is all but just calculus and algebra. And I'm going to show you some vector notation that's used in calculus a lot, and which is also used in mechanical engineering. I don't want to write the equation with so many variables. I want to simplify it. And that is done by introducing vector operator. And I'll explain what I meant by that. This operator has the symbol of upside down triangle. And by definition, that consists of a partial derivative in the 3-dimensional ijk. Operator meaning a procedure that I make differentiation of what? Well, you have to tell me what you want to obtain as a gradient. Gradient, rate of change with respect to distance. Remember the pressure gradient, dP dx? So this is kind of a nomenclature or notation that allows us to represent some kind of vector gradient. It could be pressure, it could be velocity. This is nothing but just an operator. And as such, when I form this dot product, this is the triangle. This is all in your notes now that I have posted yesterday. So this is all relatively dry algebra trying to introduce the final form of the equation in a much more convenient form. So I do it once in this detail, and moving forward, I will let you do all the interpretation on your own at your leisure at home. So this vector, and you can see already the board is filled with all this chicken feed. And then this is nothing but not even continuity. And when we go to momentum, if I have to write down everything in excruciating detail, you fill the entire board. Questions?
Do not write like a vector symbol over the operator.
I'm sorry, say that again?
Do not write like a vector symbol over the operator, like over the del.
I don't understand the question. So first I define what I meant by this upside down triangle, which is an operator that obtain or allow me to calculate so-called gradient. Gradient in terms of space. And it's defined as the unit vector and the partial derivative with respect to x and then y and z. So using that definition, I have now my operator on the right, and I form the dot product, that's what this is for, of the velocity and this gradient. And so the right-hand side, just by definition, and I need you to help me to tell me what is the result of this dot product. What is I times I? What is I times j? What is I times k? So on and so forth. So what is I times I? Remember? 1. And it becomes u. Partial of that quantity, you tell me what you want and I will put it there. Could be velocity, could be pressure, could be anything. And then I dot j, 0. I dot k, 0. It's all from your calculus. So only one term resulted from this dot product. Likewise, if you look at the other j and k direction, this dot product resulted in something that I can use later on to simplify the presentation of my equation. How? I have term that looks like this in here, and I have this operator that present term that looks similar to what I have seen in the total acceleration. And what I will do then is to take this operator of velocity dot the gradient and operate on the velocity itself. And what resulted, and it's worth to go through this in detail for the first time because it's so foreign to us. What does that remind you of? When I form this rather impressive looking vector operator. What does that remind you of? Convective acceleration. Very good. Right here. By introducing this vector notation of a gradient operator, I have reproduced this so-called convective or spatial acceleration. Do you see that? This is algebra. If you're not catching on, don't worry, go home at your leisure, look at that in more detail, it all click. I'm spending time in the lecture to go through this, but for the first time, because moving forward, all this notation will be used throughout differential calculus. So all that fancy footwork, I haven't changed the physics. The only consequence of all this manipulation is to be able to present the total acceleration in a little slightly format that you can impress your roommate who may be major in, I don't know, hotel management. Their homework is to go to the bar and taste beer, and your poor girl and boy have to deal with this. Do you get it? I know it's a little bit dry, but it formed the foundation of which we're going to now go to deep dive. So when I talk about acceleration, F equal to ma, that's my A. Not just rate of change with time, but it has a spatial component. And all this fancy footwork is just allow me to write the equation in a more elegant form. And when you do more advanced engineering work and you use a commercial code, CFD from software called Fluent, you name it, that's how the manual is written in terms of all those equations that they programmed in the computer. All right? So, let's now start to look at, with all that as a backdrop, what does the continuity equation look like? First start with application and then the derivation. So let's remind ourselves what differential equation, or what rather the control volume continuity equation look like, first and foremost. So at the end, we're going to use that equation as the starting point to alter it, change it, so that I can use it for differential analysis. Just to remind ourselves, we are now dealing with a 3D problem, no longer 2D, like the Euler streamline, but we have x, y, z coordinates, and the velocity component, just as a reminder, is shown as UVW. So control volume, that's what we did 3 months ago. It's a integral or a global approach where you show me a control volume. I will conclude that to conserve mass due to the fact it has flow entering and leaving, my control volume, my continuity equation look like this. Remember that? Final is coming in 3-4 weeks, so this is now coming full circle. And as a reminder, this last two terms, we have presented a slightly different notation then. And the time you look at that alternate presentation, you're asking me, why am I wasting so much time in showing you the equivalent term for the mass flow in and the mass flow out can be represented by this. Do you remember that? Can you read to me what all this is and the significance of the integral, the significance of dot product, etc., etc.? Do you remember that? Why is the integral needed over a differential area? Why? To account for what? Change in velocity, maybe a little bit more correctly is, go ahead.
Non-uniform velocity over the...
Non-uniform velocity. If at the station, at the inlet velocity is not uniform, why would they not be uniform? Well, the boundary there. That's what we're dealing with now. So we have to integrate. What's the significance of the V dot N? Don't remember? What's the relationship between the velocity and the area? Velocity, area. Have been perpendicular. Okay? All this is now coming back in full circle. This now a notation. We will now use those to come up with the dot dot dot, which is what we will do after all the example, and you take about 15 minutes, so that when I'm done, the equivalent equation of continuity in the differential form will look like the following. Nope, this is a differential form. It's the cousin of this equation, but the dot 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 represent the derivation that we have to go in a deep dive of an element of dx, dy, dz using this control volume formulation to come up with the differential equation. So this is an equation that must be satisfied on all the cell or mesh that I created in my domain, like the flow inside a gas turbine engine. And this equation must be satisfied at every point. All right? So now we're just focusing on the application by way of example, should a better feel for it, and then we dive into the derivation. What I'd like you to, I want to challenge you when I do start the derivation and end with it before the lecture is over, is for you to tell me what assumption will be needed to go from this step to this step. So when I come to that derivation, I will remind you of the challenge again. All right? So that will be interesting. Okay, so first look at some special cases of this general equation in differential form for continuity. What if I tell you the flow is steady? So some special simplified cases just to get a hang of how the equation can be used. Steady problem, how would you simplify that equation above? What can be paused? Steady. No? Yeah? The first term, anything relative to t is 0, or specifically in this case. So for steady problem, of which most of our problem here will be steady, will be pretty simple. And some of your homework requires you to use this formulation. Right? Do all the velocity given in terms of u, v, w, just like you have done in chapter 4. When you plug into this equation, do they give you 0, meaning they satisfy the continuity equation? If they don't, then you have a violation of continuity equation. More special cases. What if I tell you the density is constant? How would that further allow you to simplify the problem? Incompressible, constant density. What happened then to partial of all with respect to time? What would that equal to?
0.
It's 0 for a different reason, not that it's steady, but because the density is constant. And what remains is even simpler because I can factor out the density. So those are some of the special cases that will allow us to have to simplify the differential equation of continuity. And the last form is what we will do when we come back from Thanksgiving, to use that to solve the boundary layer flow. Because we are always assuming steady flow and constant density. So this reduced differential equation of continuity is one of the starting equations that we have to satisfy. All right? Any question on this simple application? So for that, let me give an example just to whet your appetite on how all this may be used for problem solving. So the example consists of a 2D flow, so not 3D, and it's in the XY plane. So I only concern myself with U and V, no W. Yes?
Just to be clear, is the first term a rho or a p? Like it's a d rho dt or
Right
d
here?
rho dt? Yeah.
It's a wall. It's a wall, okay? So you have to, at time, go ahead.
Wouldn't the one on the top be pressure?
No, there's no pressure. So let me go back. So this is all what? What's this symbol? Are you sure rho or P? Rho. They're all rho. There's no pressure. So my penmanship is very bad. I mean, my resident always say that my handwriting is like chicken feed. And to make the matter worse, my pronunciation is also not very good. So when I say P, pressure and pressure, for me, it sounds the same. So bottom line, listen to what I mean, not what I said. Okay. So I used to have a roommate in college, and I had problems saying B and R. His name is Reggie with an R. So I was an FOB. You know what FOB is, right? No? FOB? No? Well, you should watch TV. FOB, Fresh of the Boat. So I used to say, Reggie with a V, phone call for you. That was back when the payphone in the dorm. So since then, well, so since then we were never friends again. Okay, so listen to my penmanship, or listen to what I say. And I don't know how many of you heard of a beer. When I was in college, it was very cheap. I think it still exists. It's called Schnitz. Schnitz, anyone heard of that? No? Well, back then, that's all I can afford. So I'll go to the bartender and say, can I have a bottle of shit? Of course you can. Anyway, so when you have a question, please just raise your hand and ask. Yes?
So for your steady case as well, so are you assuming that your rho is a function of where you are in space as well?
For the steady case, the rho can be, since you're not always incompressible, the density can change. The answer is yes, the rho can be a function of x, y, z, unless you were told otherwise. Yeah, correct. Yes, and it happens. There's a steady problem where the flow is still compressible. It happens all the time. So you cannot factor that out of the equation. Yeah, very good. All right, so let's see how the example will work out. So I have a 2D problem whereby the velocity is given by this expression, function of x and y. And you are told for that, find me the corresponding u velocity, assuming it's steady, constant density, and then I have to, and it goes without saying, satisfy the continuity equation. So it's a very academic type exercise, but all it does is allow you to appreciate the need of satisfying a differential equation of continuity, and how do you use that equation on the right to answer this problem. So which one of the form that we have for the special cases will you choose to use? And furthermore, what else you can do to even further simplify it? So we have the general equation that is shown here, and then I have some special cases. Which one will you pick and why? Steady, constant density. You want to start with this one? A. The next one, B or C? C. With one further simplification. Well, why C? Because you're told it's steady and it's incompressible. So I have this final equation that's all a stripped down, bare bone version that specifically applied to this problem. Right? With one additional simplification. What would that be for a 2D problem? What can you do? What can you simplify? W, because it's 2D, is 0. So I have now a very simple equation that I can apply with the du dx is what I would like to integrate to get my velocity distribution. And the v velocity is given in the problem statement. They must be equal to 0, and that's called satisfying continuity, no more, no less. And I think you're all familiar with partial derivative, which is pretty straightforward. Okay? So the algebra that follow, I have now the velocity u, gradient, rate of change of velocity in the x direction. That's what we call the gradient, as a function of the right-hand side, so that the integral become my final answer. Do you see that? Does that make sense? Why do I have to put a function of y at the end as opposed to just a constant? Do you see why? Well, if you're not sure, take the answer, which is this term, and differentiate that with respect to x, so that you get to this previous step. And when you do that, because of partial derivative, this doesn't have to be a constant. This could be a function of y. Because when I differentiate that with respect to x partially, that's still 0. All right? So continuity can be used to look at other components of the velocity. But this is, to be honest, purely academic. Right? This has no real life application. But it just warms you up to how the equation can be used. Yes?
If that were in 3 dimensions, would your function have to be of y and z?
Yes, correct. Yes. Okay, so your homework on problem 611, the wording of the problem is not very clear, but what it really asks you to do is the same exercise and see if the differential equation of continuity is satisfied. So that's the spirit of that problem, making use of all the partial derivative. Question. That's an application I hope get you here up to the deep dive. If there are no questions, I'll give you a 2-minute break. I'll erase the board, and when we come back, we go to the deep end of the pool.